Astronomers now confirm that 3I Atlas will pass near Jupiter on March 16, 2026, and the distance is exactly the same as the region where the object appears to be performing a maneuver no natural comet should ever be capable of. It is slowing down near Jupiter with an accuracy that looks almost intentional. The object is approaching the outer edge of Jupiter's Hill sphere, the thin gravitational boundary where the planet's pull begins to lose control to the Sun. And yet, Atlas is heading toward this line with such mathematical precision that it resembles a deliberate stop. No known comet has ever demonstrated this kind of controlled behavior, and scientists are now faced with unsettling questions about what is guiding its motion. If this is not a natural path, then what is shaping its next move? The strange journey of 3I Atlas began long before the world noticed anything unusual. It first appeared as a tiny speck drifting in from deep interstellar space, following a simple hyperbolic trajectory, exactly what astronomers expect from an object not born in our solar system. Its speed, direction, and structure all looked normal, and researchers assumed they were watching another rare visitor that would pass through quietly and leave without controversy. But after it moved closer to the Sun, something changed. The shift was subtle at first, so subtle it almost went unnoticed. Then came the moment that changed everything. A non-gravitational acceleration detected just after Atlas passed perihelion, its closest approach to the Sun. This tiny push nudged the object away from its original course, but the direction of that push was nearly perfect for steering it toward the exact position it is now approaching near Jupiter. Comets often change speed when heated by the Sun. Jets of gas shoot out and create chaotic motion. But most comets tumble, wobble, and behave unpredictably. Atlas did the opposite. It moved with smoothness, stability, and purpose. This unusual pattern led many astronomers to suspect that the object might not be drifting accidentally, but could be reacting to internal forces or structural properties we do not yet understand. What makes this story even stronger is the data. More than 200 observatories worldwide tracked the object, and every updated model pointed to the same conclusion. Atlas was no longer following a path shaped only by gravity. Each observation increased the accuracy of a prediction that seemed impossible. Its trajectory was aligning with the boundary of Jupiter's Hill sphere. The consistency across global datasets makes this deviation extremely difficult to ignore. The acceleration pushed Atlas by the exact amount required to reach its current target. Natural or not, the timing, direction, and precision are extraordinary. Even stranger, Atlas showed no signs of instability as it approached the inner solar system. Many interstellar objects break apart under solar heating, but Atlas remains stable, smooth, and intact, suggesting it may have an unusual composition or internal strength. Taken together, these clues show that the maneuver unfolding near Jupiter is not random. It is the final step in a long sequence of small, coordinated shifts that began months earlier near the Sun. And now comes the most astonishing detail. Atlas is expected to pass Jupiter at a distance of 33.242 million miles, yet current measurements place it only 35,000 miles from the exact balancing point of Jupiter's gravity. The margin of error is 1 in 26,000, a level of precision rarely achieved even by engineered spacecraft. To grasp how shocking this is, imagine throwing a needle from Los Angeles and having it land precisely on the edge of a coin in New York. This kind of perfect alignment almost never appears in nature, especially not from an object that has traveled billions of miles across open space. The significance becomes even clearer when we compare Atlas's behavior with that of typical interstellar objects. Most visitors from deep space enter the solar system spinning unpredictably, with uneven surfaces that heat at different rates. Even tiny patches of sunlight can push them in chaotic directions, making their final path extremely difficult to predict. With the best models, astronomers normally expect wide uncertainty zones, not narrow ones. But Atlas has broken every expectation. With each new update, the margin of error has shrunk instead of widening. This tightening accuracy is more than a scientific curiosity. It strongly suggests that the object is following a clean, stable, and unusually consistent line, unlike the noisy drifting behavior of natural comets. The numbers reveal something even stranger. This precision didn't slowly build over time. It began sharply right after Atlas passed close to the Sun. A tiny, almost invisible acceleration nudged it off its original track. But the correction was exactly what was required for it to slide into the narrow region surrounding Jupiter's Hill sphere. Had that push been even slightly weaker or stronger, Atlas would now be millions of miles away from its current target. The odds of a natural force producing the perfect strength and direction at the perfect moment are extremely low. This is why so many researchers are questioning whether simple physics is enough to explain the motion. The effect resembles a steering adjustment, the kind used in spacecraft navigation, far more than a random cometary gas burst. The alignment becomes even more intriguing when we consider the location itself. The outer edge of Jupiter's Hill sphere is not a place where natural objects typically wander. When comets approach Jupiter, they are usually pulled inward or flung outward. They almost never drift along the thin mathematical boundary where gravitational control shifts from Jupiter to the Sun. And yet Atlas is not falling toward Jupiter or veering away. Instead, it's sliding right along the line, a behavior that appears almost deliberate. In many ways, the motion looks like a controlled approach, ending at a gravitational balance point more familiar to engineered missions than aimless debris. When we combine the tiny trajectory error, the razor-sharp correction near the Sun, and the unusual target, the truth becomes hard to ignore. This is not a normal trajectory. Something is keeping Atlas aligned to a single, precise mathematical line across tens of millions of miles. If this is coincidence, it would be one of the rarest ever documented. If it's not, the implications are enormous. This brings us to a critical question. What kind of process can guide an interstellar object with such perfect timing and accuracy? To answer that, we need to understand why Jupiter's Hill sphere matters. This structure marks the region where Jupiter's gravity becomes stronger than the Sun's pull. And for a giant like Jupiter, the zone stretches across tens of millions of miles.
Most natural bodies never strike this exact boundary because their paths are shaped by chaotic forces, solar heating, collisions, random jets of gas. They either fall deeper into Jupiter's gravity or stay well outside its reach. This makes the Hill sphere's edge more of a mathematical line than a physical destination. So the fact that Atlas is aiming for it with surgical precision is already astonishing. The boundary is unique. Forces inside are dominated by Jupiter, while forces outside are controlled by the Sun. A slight change in speed or angle can create two completely different futures: capture or escape. Because of the sensitivity, it is extremely rare for any comet to match the exact distance where the gravitational powers balance. Natural bodies do not slow down or adjust direction in such a controlled manner at this line. The comparison becomes clearer when we consider how space agencies use gravity. Engineers rely on Jupiter's deep gravitational well for slingshot maneuvers that require precise calculations. Even a few thousand miles of error can drastically alter a spacecraft's future trajectory. Reaching the Hill sphere boundary with fine accuracy is difficult even for human technology. So seeing an interstellar object match this precision raises major questions about the forces shaping it. Another striking detail is the thinness of the transition region. Although the Hill sphere itself is enormous, the exact boundary, the tipping point where control shifts, is incredibly narrow compared to the surrounding space. Hitting this line is like trying to land on the moving edge of a shadow. Its position shifts slightly with every orbit, making Atlas's alignment even harder to explain through random chance. The more the data is refined, the clearer it becomes. Atlas's approach is far too clean, too stable, and too consistent for a natural body that has wandered through interstellar space for millions of years. This leads to a challenging question. If the Hill sphere is not a natural stopping point, then why is Atlas positioning itself so perfectly along this invisible border? The idea of a precision parking maneuver becomes more understandable when we examine how the object changed direction after passing the Sun. That slight push acted like a course correction, almost identical to what a spacecraft would perform when fine-tuning its route using minimal energy after perihelion. Atlas then followed the corrected line with astonishing stability. No wobbling, no drift, no chaotic jets. Natural comets experience irregular bursts of gas that usually disrupt their motion, not perfect it. But Atlas has not shown this chaotic behavior at all. And the timing of the correction is another reason researchers are paying attention. A shift made earlier or later in the journey would not place Atlas at its current target. The adjustment happened at the perfect moment in a dynamic solar system full of moving planets, shifting sunlight, and destabilizing forces. A normal comet would normally be pulled inward or pushed outward long before reaching this region. Yet Atlas is gliding along the boundary with an unusual, almost unnatural stability. This stability suggests that the object may possess physical properties that allow it to remain balanced in ways most comets simply cannot. Once we put these pieces together, the picture becomes even more mysterious. The shift near the sun, the stable route, and the unusually precise target all resemble the outcome of a carefully executed adjustment. If this were accidental, the chances of everything aligning so perfectly would be extremely small. And if it was not accidental, then the question becomes far more serious. What kind of internal process could produce a maneuver that looks so much like a planned action? The puzzle of what is guiding 3I Atlas becomes even more complex when we examine the four main explanations scientists have proposed, each one trying to describe a scenario with almost no precedent in known astronomy. The most conservative explanation is observational error. Early measurements of fast-moving objects often contain small inaccuracies. But in this case, more than 230 observatories have tracked Atlas, and every new dataset continues to confirm the same trajectory with shrinking margins of uncertainty. This high level of agreement makes the error scenario increasingly difficult to support, especially because Atlas keeps matching predictions with remarkable precision. A second possibility is rare but natural outgassing. Heating can activate jets of gas that push a comet gently in one direction. If these jets line up with cracks or weak spots on the surface, they can create motion that appears more organized than random. The problem is that these jets would need to fire at exactly the right strength and angle for a very long period of time. Even a tiny deviation would send Atlas drifting far from its current target. The chain of coincidences required makes this scenario possible, but highly unlikely. A third explanation is coincidence. The solar system has existed for billions of years, and countless interstellar objects may have passed through unnoticed. If even a few of them crossed paths with Jupiter's Hill sphere purely by luck, Atlas could be another example. This isn't impossible, but the rarity of the alignment and the clean, unwavering path leading to this moment make coincidence a weak answer. The fourth and most debated idea suggests that Atlas might be reacting to forces in a controlled or semi-controlled way. This does not automatically mean the object is artificial. Unique structural or chemical properties could allow it to use sunlight, gravity, or internal processes to guide itself without technology. Some researchers have even suggested that an advanced civilization, if one exists, might navigate through planetary systems using gravity wells and boundary zones like Jupiter's oosphere. There is no direct evidence for this, but Atlas's behavior keeps the question alive. These four explanations form a map of possibilities, yet none of them close the mystery. If the answer is not error, coincidence, or ordinary outgassing, then what kind of process could be producing such a steady and precise journey? Jupiter has always held a unique place in the solar system. Understanding why 3I Atlas is heading toward this giant world helps explain why some scientists believe its current path might involve something far more complex than simple physics.
Jupiter is the largest planet we have, and its gravity is so powerful that space agencies routinely use it as a natural engine to redirect spacecraft with minimal fuel. A single close pass can speed up a mission, slow it down, or send it on an entirely new trajectory. For this reason, Jupiter is often called a navigation gate. Its gravity well shapes the motion of anything that enters its influence. The outer edge of Jupiter's hill sphere is even more important. It marks the exact region where Jupiter's pull balances the pull of the Sun. Here, tiny changes in speed can produce major changes in direction. These sensitive balance points act like stepping stones, locations where spacecraft can hold stable positions with extremely little effort. Engineers spend decades calculating how to reach these zones. Even with modern technology, it requires precise timing and razor-sharp navigation. And yet, Atlas is approaching this region with a level of smoothness and stability that is difficult to ignore. Jupiter's gravity well also allows any object, natural or artificial, to travel through a planetary system with minimal energy. If an object wanted to conserve power, gather information, or transition between trajectories, this boundary would be a logical place to pass through. Natural objects entering this zone often experience dramatic gravitational effects. Atlas, however, is approaching it with a remarkable calmness that suggests more control than chance. Even more intriguing is the apparent slowdown Atlas is showing near this region. A slowdown near the hill sphere could indicate preparation for another shift, perhaps a change in direction, a temporary pause, or an interaction with the gravitational landscape that produces a new trajectory. These possibilities make Jupiter a crucial part of the mystery. The planet creates an environment where tiny forces can lead to enormous consequences. If Jupiter truly operates as a gateway deeper into the solar system, then the question becomes inevitable. What will Atlas do when it reaches the edge of this massive gravitational frontier? As 3I Atlas approaches Jupiter, scientists believe three major scenarios could unfold in the coming weeks, each with the potential to reshape our understanding of interstellar visitors. The first scenario is fragmentation. As Atlas crosses the edge of the hill sphere, the competing gravitational pull between Jupiter and the Sun may create intense tidal stress. Many comets crack or break under such conditions. If Atlas fractures, we may finally get a clear view of its internal structure, something no telescope has yet been able to reveal. If Atlas contains layers, hollow regions, or unusual materials beneath its surface, a breakup could expose them, offering the first direct evidence of how an object from another star system is built. This would give scientists a rare chance to study interstellar debris up close, but it would also raise a deeper question. How did such a fragile structure survive its long journey through interstellar space? The second scenario is even more mysterious. Some researchers suggest that Atlas may release smaller bodies or particles as it slows near Jupiter's boundary. Natural objects do shed fragments, but doing so at a gravitational transition zone would hint at a process far more organized than simple erosion. If Atlas releases small pieces that settle into stable orbits or drift in coordinated patterns, astronomers will analyze the shapes and motion of these fragments to determine whether they behave like ordinary comet debris. Any pattern that looks too clean, too deliberate, or too synchronized would challenge our understanding of what an interstellar object is capable of. The idea of a payload release sounds dramatic, yet even a small cluster of fragments moving with shared direction or timing would spark serious discussion about why Atlas is here and what purpose such behavior might serve.
The third scenario is the most surprising. Atlas may change direction once it reaches the outer edge of Jupiter's domain. A shift in motion at this point would imply that the object is responding to the gravitational environment in ways that do not match the behavior of a simple comet. If Atlas turns onto a new path, slows down further, or briefly enters orbit around Jupiter, scientists would gain powerful evidence that its movement is influenced by more than random forces. Even a slight adjustment could become one of the most important clues of this entire investigation, something that resembles the fine-tuned maneuvers of controlled spacecraft. These three scenarios highlight how extraordinary this moment is. Each possibility, Fragmentation, fragment release, or directional shift could reveal different secrets about Atlas and the forces guiding its journey. Whatever happens next will reshape the questions scientists ask about interstellar motion. At this stage, the voyage of 3I Atlas feels less like a random passage and more like a sequence of deliberate steps. Its precise arrival at Jupiter's boundary suggests a kind of purpose that natural objects rarely display. The alignment, the timing, and the calm approach all point toward a moment of profound importance. If this stop was intentional, then the next move becomes the mystery that matters most. What is Atlas preparing to do once it moves again? Share your thoughts below, and don't forget to like, share, and subscribe for more investigations.